What's up? Today we have yet another math problem. So it's this one is actually kind of difficult, but I think you'll get it. So find the sum of all numbers with digits 1, 2, 3, 4, 5, and 6. And that means using all of them, but no one, but none of them twice. So, for example, we have the obvious choice 123,456. This one, and an option I can just give you is also 124,356, and so on. So we have all of these different combinations, and we have to calculate the sum of them. Oh my God. Okay, I'm sorry. This problem is not hard at all. I'm just retarded. Okay, I can just tell you quick what I was gonna do up until right now. Fuck. I was thinking like, okay, if you put the if you, okay, if you know you have a one here, and then all the other ones are no, I'm kidding. No, we have to do it that way. My new method doesn't work. It isn't the sum of the digits, it's the sum of the actual numbers. So we still have to do that. Yes, okay, good. Good. I'm on track. Yes. So, um, so how do we do this? Well, as I was going to say, we have to regard, we can just, first, we start by thinking, okay, if we have, we just think about the first digit. That's all we do. Okay, so we know that, okay, in how many cases is there a 1 in the first row? And the first row means, well, it's 100,000, so it's 10 to the power of 5 times, okay, and how many combinations can we create? How many numbers using this can we create where we have a 1 in the front? Well, for this one, it has to be a 1, and for that, we can choose between 2, 4, 3, 5, and 6. So just becomes a 5 factorial, and yeah, we have 5 choices here, and 4, and 3, and 2. So it's 5 factorial. Yes. And then, if we instead think about this, okay, we have a 2 in front. So then that is equal, and because we're counting the sum, so it's basically the same as just counting the digits, but with the respect to where they're standing. So we take a, yeah. So in the example where we have 2 now, we still have to take it to the power of times 10 to the power of 5, and it's the same thing there. It's also 5 factorial, and well, yeah, maybe you can see the pattern, and then if we have a 6 in front, we have 6 times 10 to the power of 5 plus, sorry, times 5 factorial. So, okay, so this is the first case. We have, we've just counted what the first digit is. And just to make sure, we can look at this and think now, okay, how many possible cases are there in total? Because we're just multiplying it because that's the digit we're choosing. But if we disregard that, how many do we have left? Well, we have, okay, 1, 2, 3. We have 6. 6 times 5 factorial. That's 6 factorial, and that's how many different combinations you can make, obviously. So yeah, so this is the sum of all the first digits and all the possible combinations. And then for the second digit, we do basically the exact same thing, except we have a 10 to the power of 4. And yeah, everything is the same, and 10 to the power of 4, and everything is the same, except 10 to the power of 4 here also. I can write that. And then we keep on going down here until we just have to the last digit, which is just 10 to the power of 0, which is just 1. So we at the last stage we have 5 factorial plus 2 times 5 factorial plus all the way up to 6 times 5 factorial. Okay, so we have quite a lot of terms. More specifically, we have, okay, in this way we have six rows, and we have um, yeah, we also have 6 columns here. Yeah, exactly. Yeah, 6 rows and 6 columns. So we have 36 terms in total. But how can we simplify this? What pattern do we have? Okay, for each row, what is constant? Well, the exponents are constant. And then it diminishes by 1 step for every new row, right? And then for each column, what do? Well, yeah, we multiply by 1, and then 2, and then 3, 4, 5, and then 6 here. So we should be able to rewrite this with a sum. And I'll do that real quick. So yeah, now that I erased it, might get a bit confusing, but you can jump back and look at the whole thing. Okay. So what did we have? We had that the exponents were constant on all the rows, and the factors were constant in the columns. And we're supposed to calculate the sum of all of them. So what is this? Well, okay, we have the exponent changes and the factor changes, and we have every single possible combination. So therefore, we have a sum within a sum. So yeah, we can call it, we had rows and columns. We can use that. So we have that the row went from 1 to 6, and the column also went from 1 to 6. And what was it saying everywhere? We had the factor times 10 to the power 10 to the power of something, and then times 5 factorial. So we can just start with the 5 factorial. We have 5 factorial here, and then we had times, okay, it was 10 to the power of what? Okay, the exponents were constant in the rows. So yeah, we'll take that to the power of the row, and then multiply that by the factor, which was just the column. Yes, so this is our formula. If you can calculate this, we're golden. So firstly, we can just extract the 5 factorial from the sum, because that's just a constant term. Here, we had kind of the same thing as a previous video, in which we have, okay, within the sum where c changes, r is a constant. So we can extract that in the front. So I'll do that. And suddenly this looks a lot nicer. So then we'll just start from the inside out. What is the sum of 1 to 6 of just C? Well, that thing, you can do it as like this. What is this sum? This is, okay, it's 1 plus 2 plus 3 plus 5 plus 6. So that should be, well, it's 7 times 6 over 2, which is equal to 21, which makes sense because it's 1, 1, 3, 6, 10, 15, 21. Yeah, exactly. So this inside is 21. And since this is a constant, we can just move that outside. So what do we get now? We get 21 times 5 factorial times a lot smaller sum now, because we remove things, 10 to the power of r, where r goes from 1 to 6. And for this, you can either use the geometric sum formula, or you can just think. So okay, we have. Um, no, I'm so sorry. The R shouldn't go from 1 to 6. R should go from 0 to 5. Oh my god, I'm stupid. I'm so sorry. Uh, Sorry if that disturbed you. If you were smarter than me and realized. Yeah, exactly. From 0 to 5. So what we have? We have 1 plus 10 plus 100 plus 1000 plus 10,000 plus 100,000. What is that? That's just a bunch of ones. So this thing should be 21 times 5 factorial, and 5 factorial is 120, and then times just 1, 1, 1, 1, 1, 1. And this answer, this is our answer. If I could calculate it in my head, which I will not. So wait. So I'm back. And now this thing appears to be, according to my calculator, 279,999,720. And that is the sum of all possible uh, integers using the numbers 1, 2, 3, 4, 5, and 6. So, well, yeah, I really, really like this problem actually. I think it's a lot of fun, especially when you can like write it out with the rows and the columns. It really simplifies it so much. It seems so daunting at first, but it isn't that hard. So yeah, that was all for me. Hope you enjoyed the video. That was yeah.